So let's go back to this. So we have the while statement just now with the example. Next, we will look at this example, the practical example where we want to move a block of data from a memory address location 20000000 until 2000 to 001F, right? Means that the data is in between this location to this location to a new location from this 20000020 until 20000003F. So we want to write the program to do this operation, right? So first thing, when we want to write a code in any programming languages, first thing that you need to do is to plan your program, to plan your code, to have the planning. Uh, the uh, the planning can be in the form of pseudocode or in the form of flowchart. Yeah. So most of the time we use the flowchart, right? So this is the example of the memory content that we want to move into a new memory location here. So this is a block of memory from this until this, and we want to move or copy to this location, all right, such that we can have the same data here. Okay, so this will go to this location, this from this location into this location till the last one here. And when we look the memory, uh, the illustration of the memory in the software, in the Kale software, it is displayed like this, right? Just like this, yeah, in this view. So what we can do is, or need to know, is the size of our data, all right, from location 00 to 0000 here until 1F here. So it is 8 word size, 8 word size, or 16 half word, or 32 byte, right? 32 byte. So with this information, we now can write our program based on this planning and the flowchart. Yeah. So remember, when you want to write the program, start with the plan. Yeah, and this is the plan, the flowchart. Okay, because when you write the program, when from the specification and you start to write the program without the plan, and I can say that I can guarantee that the program will not work. All right. So the best way is to have your plan. So this is how we plan the program using flowchart. So first thing we need to do is to have the address for the data. In this case, we use R0 to store the address of the data starting from this address 20000000. And the destination address, the destination, the location that we want to move our data into is in art1, right? Which is this. Yeah, remember this, the first location of our data. And we have the counter. So this counter will count to up to 8 words, because we have 8 words to move. But if you use half word, it means that if you transfer the data one time in half word, so you need to count up to 16. But if you transfer your data byte by byte, you need to count up to 32, right? Because this is 32 byte or 16 half word. In this case, the best way is to use word because we have the option to move the data in 32 by 32 bit in size at one time, right? Or one word here means that we can have this data from this to this go to here, and then the next word go to here, the next go to here, and so on, right? So it will reduce the size of your program. So in this case, we use uh, word, yeah. And now we move the data from memory to R2, right? Because in ARM microprocessor, you cannot move directly from memory to memory, right? You need to load the data to the register, and from the register, you send to the new location in the memory, remember? So you need to load the data first to the register. So you have many registers. You have R0, you have R1 until R12 for general purpose register. Use one of them uh, to be a temporary data storage. Yeah. So in this case, I use R2, right, to get the data from the memory location from the source here, put in R2, and then I update the value of R0 here, the value of R0 by 4. Why 4? Because 4 is one word. Yeah, if you update by 1 means that you update by byte. If you update by 2 means that you update by half word. If you plus 4 means that you use word, yeah, word or 4 for byte. So I update with 4 means that R0 plus 4, you have 20000004 means that this address, the next word, here, plus 4 again, the next word. This is mean by this. And after we update this, we move from the R2 into what is pointed by this R1. R1 is this. So we move to this location. So the operation will be like this. Yeah. So let's have this thing. This is my memory. Second location, second block. This is the first block. This is address. This is the next one. The next one. This is 21, 22, 23, and so on. So my data is here. For example, I have I want to move to here. So the first word, yeah, right. When I write the code like this, LDR R2, is it in R1? This one is in R1. So my R1, I have And in R2, I will get this value. I will get this value in R2 when I do this. So my R2 will have this. So it will be 1, 3, 1, 2, 1, 1, 1, 0, right? In R2. And from that, I store back into the new location. So I used str. In this case, this is R0, sorry. This is R0. So R1 is 20, the 21, the destination. R0. So this will be R0. Now I store in what is pointed in R1. So I will get in R1. Next, I will go to the next location. So how to do that? Because I plus R1 with 4. And here also I update R1. R0, here is R0 by 4. This is R1 by 4. And I increment the counter, R3, from 0 to 1 and test. Oh, this is not 8 yet. And I need to go back and get the new value to R2. So the new value now is not this anymore because I plus with 4. So it will be 200000004, right? So it will be here, which is the new word here. And again, put in R2 and send to the new location here. Send to a new location here and update the counter until the counter equal to 8, means that the last location already. If 8 already, then we end the process and we can get the value, right? So this is the assembly code. So use move W and T to get the value in R0, the pointer for the first block. You can also use the LDR R0, right? So instead of 2 instructions here, you can use only 1 instruction using this. We have just learned just now. We can use LDR R0, okay, to get this value in R0 in one single instruction. Right? But if we use this, we need to use 2 instructions. We use move. This is the way, and this is for R1 to get this in R1, and this is for the counter have 0 in R3, and this is load the value pointed by R0, which is here, into R2, and after that plus with 4 in one instruction using the post index addressing mode. So this is this using in one single instruction, means that after we move the value here from memory location here into R2, then automatically we add 4 to R0, right? And then we store R2 into what is in R1, which is this address, R1 here, this address. And again, we update the value in R1 by 4 plus 4, so that we go to the next one after this. And here is to update the counter, right? We add with 1 and we compare whether it is equal to 8 or not. If not equal to 8 yet, right? So you can go back to li and do this again until here, and we exit the loop here and done, right? So that is how we uh, move blocks of memory content to the new location, new blocks of memory. Simple. The next one is to uh, what we call a normalization, or in other words, we want to have in R0 or this value, we want to normalize this value where we want to have the MSB is equal to 1, means that we need to shift left until we have MSB equal to 1, right? So the best way is to have the flowchart like this. We check MSB equal to 1 or not. If yes, done already. But if MSB is not equal to 1, so we shift left, check, not yet, go back, shift, check until MSB equal to 1 and we end. So in the program, we can do just like this. Move the value that we want to check into R0, and we move as to R1, move as. This is move variant of move instruction as, means that we move and we set uh, the status flag, yeah, based on the number that we have in R1. So in this case, because our R1 is 32-bit, so when we execute that instruction, we will have in R1 is, this is our R1. When we move this into not R1, R0, sorry, R0, and then we move to R1, yes, yeah, the second one. So we will have in R1 is 0, 0, 0, 0, 1, 2, 3, 4. So the flag we have NZVC, right? So it will set this flag. So definitely the N is equal to 0 because the MSB is 0. Z is 0 because it is not 0. V is not related, actually unchanged, or 0. C also 0. That is how the MOVS work, right? So we move to R1 and we check BMI is what? Branch if minus. BMI, if we go back to this MI, BMI is branch if minus or negative or N set, right? So in this case, if minus, done. If negative already, so means that done, because we want to check MSP equal to 1 or not, right? So done. No need to do this. But if this is not negative, so we need to shift. So this is how. This is logical shift left. As it at the back means that we update the flag after we do the shift. So logical shift left, what you do is you shift left one bit at a time. So this is 1 bit. So what you do is that when you shift 1 bit, you will have in R1 is what? When you shift 1 bit to the left. So this is 32-bit, and the number is quite big. So let's have 32-bit number. Quite big. And we have 0 1 0 0 for number 4. So this is 0 0 0 0 1 2 3 4 in hexadecimal. And when you shift to the left one bit, what you can get here is still 0 0 0 0. And when you shift, this is of course shifted out. This is shift, 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 shift. You have 1 here. This one shifted here. And you have 1 here. And you have 1 1 here. And you will have 1 0 0 here. Right? And the number in R0 will be 0 0 0 0 2 4. This one is 6. This one is 8. 6 8 2 4 6 8 when you shift one time. And of course the MSB is still 0. MSB is still 0. So when BMI branch is minus, if minus V branch go to done, but in this case one time still not minus yet, so you need to go to LI, repeat, shift again. This one is shift again, so you shift the bit again, shift again until this uh, until this number 1 here go to the MSB, shifted to this location, then it will stop the loop, exit the loop. So that is what this program do. Okay, very straightforward. All right, any question so far? No, now is no question. I think stack and subroutine we should continue next week. I want to discuss a little bit about your assignment here. Okay, we still have time for this stack and subroutine next week. So, but before that, let's do some exercise and let's discuss about the assignment. Okay, let's discuss this. We have another half an hour, right? About 34 minutes. So let's look at the exercise. Number 1, write a question. Write a sequence of instruction to clear bit number 7 to 0 of register R0. How to do that? So we have this in R0. We don't know what is inside R0 initially. Right, let's, for example, this is our R0. What we want to do is, so let's say inside this R0 we have unknown value, hexadigit, 32-bit value. And what we want to do is we want to clear bit number 7 to bit number 0 in register R0. So where is bit number 7 to bit number 0? Means that these two hexadigit, right? Because bit number 7 to 0 is 8-bit size. So it should be these two. So these 2 bit you need to clear to 0 without affecting any other bit. Means that here should remain the same. That is what we want to do. So how to do that? Any idea? Uh, okay, the question is how to clear. Okay, so Divaka said move 0, 0 into what? Into R0, is it? So if you have this instruction, for example, you move 0 into R0, what happens is that you will clear all the content of R0. So what you will have is this. If you do this, you will have all 0 in R0 if you use this instruction. We don't want that. We want if, for example, if in this R0 we have this number, we just to clear this 2-bit only. This 2-bit only. Sorry, this 2-digit only. This 2-digit is 8-bit. Bit number 7 to bit number 0. So when we run our program, what we will get in R0 is this. So how to do that? Definitely cannot use this, yeah, because it will clear all the content. Yeah, Divaka? So definitely cannot use this. Any other idea? You may need more than one instruction. Okay, I give you an idea. So if, for example, in R0 we have and of course we want to clear these two bit these two, sorry, we want to clear these two only. So what we can do is we can use an operation. If we can end this with 0, definitely these two will be 0. And again, we want to preserve this content. We don't know actually what is inside R0, but we just want to clear these 2 digits. So for example, inside this is 1, 2, 3, 4, 5, 6. Yeah. So to preserve this, you need to end this with 1, right? So hexadigit for 1, 1, 1, 1, 1 is F, right? When you end with 1 with F, you will have 1 back. 2, 3, 4, 5, 6. And when you end 7 with 0, yeah, 7, 0, 1, 1, 1 with 0, you end, you will have 0. Here, when you end 1 with F, you will have 0, 0, 0, 1. You get 1 back. When you end 2 with F or 1, you have 2 back, and so on. So this is how you do. So in the assembly language, what you need to do is that you need to move W. Maybe you use R1, F 0, F 0, 0, and you move T R1, F, so that you get this value in R1. And what you need to do is you just N in assembly language is this. Remember last week? This N, yeah? So you can use N, AND, R0 with R1. Then you can get something like this, where this one will be cleared to 0. Okay, get the idea? So this concept is called masking in microprocessor or in programming. For example, the second one, what if we want to set? Now we want to set bit number 7 to bit number 0 in R0. So how to set? The previous one we want to clear. So in the second one, we want at the end we will have FF. Oops, sorry. At the end we will have FF in R0, means that all these bit number 7 to bit number 0 is set to 1 here. So we have FF. So how to do that? Before this we used N to clear. So to set is easy. You use OR, right? Because when you have, for example, any 8-bit value, right? For example, this 8-bit value we want to set all. We have, for example, this is 7, 8, right? So in binary is 0, 1, 1, 1, 8 is 1, 0, 0, 0. So we want to set all the bit. So just OR with 1, 1, 1, 1, 1, 1, 1, 1. Then you can have 1 here, 1 here, 1 here, 1 here, 1 here. 0 or with 1, you have 1, 1, 1. So here you have F, here you have F. Means that you set all the bit here. So the instruction will be, you move 0 0 0 0 0 0 in to R0 into R1 in this case. So you can have 0 0 FF, and here is 0 0 0 0, and you or in the instruction for OR is E OR odd, yeah? OR E OR is XOR OR odd. So you can use OR odd R1 R0, then you will have this FF in R0. Very easy. Okay, so that is the this. So you can try to do this. Yeah. So your assignment will be, okay, I don't want to use this as assignment, but I give you the new one. Your assignment will be this. You select one location in the memory. The size is 100 byte in memory, any location. And to know that, to know where location that you can manipulate and read or write, you may want to know why I always use location, for example, 2000, not 2000, this starting with 20000000, right? Most of the example is using this memory location in the program, right? For example, where is it? The previous one. This one also starting with this memory location. Why not using other location than this? Because we have very big memory spaces, right? For ARM, 4 GB. But why I always use 200000? So the reason is that when you use kill, here we can look at the what we call the memory organization for this, yeah. Debug memory map, yeah, here memory map. So it is set to this, yeah. So from address 20000000 until this location is read write, means that you can use, or you can use any location from this 20000000, because it is set for read and write operation. But before that, location before that, you cannot use, because this is read only, for example, right? And you can actually you can modify this, you can modify this, but in this case I just use what we have here. And this is not fixed, depend on the microprocessor manufacturer, right? What how we want to set this memory organization, right? So in the assignment, what I want to do is you select any memory location in the memory map, right, where the size is 100 byte, and you count, you go through each location, go through one by one and check the content of the memory, if you found A, so A in hexadecimal and in ASCII representation is 41. Yeah, if you look at the ASCII representation, A is 41, right? So if you found A, for example, this one is B, again you have A, and how many A in the memory range 100 byte. So you select on your own, you want to start at what location and end with one location, with what location. So I want you to count how many A you can find in this range, 100 byte range in the memory. So for example, if you find 2, the output in R0 is 2. If you find A is 10, the output will be 10, right? And of course, in your program, you need to predefine uh, the content of your data. All right, you just need to demonstrate if you have, for example, 10A, your program should be able to give you number 10. If you put 50A in this memory location, and your program will give you 50, for example, right? So this will be an individual assignment where all of you need to do. I will give the detailed description. I will post on Author, and so that you can upload your answer there also. And why I not give you the memory address, you need to choose on your own, because this is online assessment. So I don't want you to have the same answer with your friend. So for example, if you choose 200000 as the starting address, your friend should be different, and also the number of A or B or any other character that you want to find should be different, right? And also the program structure, the flowchart should be different, should be because in programming, right, you can have different different program, different flowchart, and can produce the same result. All right, so you and your friend must not be the same. All right, at least uh, has should be unique. I mean, should be unique, right? Must have different. Okay, so that will be the assignment. So this assignment will help you a lot to understand what you have learned in this course, and also will help you in the test. Okay, so we are almost 11 already. Any question before we end our session today? Okay, 11 already. Thank you. See you next week.